Let us say we have a problem to measure the length of this cable. This is network cable. So there is two ways to solve this problem. Now, the first way is complex way to unfold it and to measure it with the ruler. And the second way is simple way to use this oscilloscope or any other oscilloscope. So the solution is very simple. And in this case, I have this device with the generator, channel number 1 and channel number 2. So we connect it like this. So we connect the generator to the channel number 1, and then channel number 1 we connect to the cable. So this is the channel number 1 connected to the cable and connected to the generator. So the second end of this cable goes to the channel number 2. So pretty simple. And now let's look at the graph. So here's the graph, and those are pulses with frequency 1 kilohertz. So this is the yellow one is the channel number 1 connected to the generator, and the blue line is the channel number 2. And we should focus our attention on the front of this pulse. So let's zoom in a bit more. Yeah, so the yellow line is the channel connected to the generator. So what we can see that at this moment the pulse starts, it goes to the cable, and it reaches the end of this cable, and we see it at the end of this cable as a blue line connected to the channel number 2. So once again, the signal from the generator goes to the channel number 1, then it goes to the cable. We have this spike, yellow spike, and then through the cable it goes back to the oscilloscope to the channel number 2, and we see the blue line rising. Okay, and after some moment again we have the rise of the yellow channel. That's because the signal goes back to the initial position, so it goes back through the cable to the channel number 1, and it takes twice the time. So basically the first moment is when we have the signal going through the cable reaching the end, and the second one is when the signal is coming back to the initial position, and then it's repeat itself, so reflects back and forth. But that's all we need. So by measuring this distance, we can say how long it takes for the signal to travel through the cable, or we can measure this length when the signal goes back and forth and divide by 2, and we're going to get the time needed for the signal propagation through this cable. So I have put the cursors on, and now we can move those cursors to the position that we wish. Okay. So the first position is here in the beginning of the signal, and the second position is here when the signal is reaching the end of the cable and is observed on the second oscilloscope. So the signals start from here, the yellow part. To move it a bit more to the beginning. Okay, so this is the initial moment, and then the signal goes through the cable and reaching the end of it, and you can see it on the second channel. So the blue line is rising. So this is the distance, and here is the time, approximately 240 nanoseconds. And if we move this cursor to this position, number 3, so we're going to have approximately 490 nanoseconds, 486 nanoseconds. So twice the time needed for this propagation. And because this observation that round trip takes twice the time, surprise, surprise, we can actually remove the second channel entirely from the picture. So we don't need the blue line, the yellow line is sufficient. So there is no need for the two-channel oscilloscope. You just can have any single channel oscilloscope for these measurements. And because we need second channel, we can just remove it. Done. But we need something else to continue our computations. We need to know the impedance of this cable. So how to know the impedance of this cable? It's pretty simple actually. If you terminate this cable with a potentiometer, let's say this one, and you will reach the point at which by rotating this potentiometer you're going to measure the impedances. So in that case, there is no wave is going to be reflected back to the cable. So the wave goes from the generator to the cable and is going to die in this potentiometer. So nothing is going to back from it. Like a black hole is going to consume all the energy from the cable. This is 1K potentiometer, and at this position it has the maximum value, 1K. And here is the graph. So now I don't have the blue line, I have just yellow line. So this is the moment when the pulse is coming to the cable. This point where the pulse is reflected, where the pulse is reaching the end of the cable, and then it travels back, reflected from the end, travels back to the initial position, the beginning of the cable, and then we have spike again. So at this moment I'm going to move this potentiometer. So I'm moving it, decreasing the value of potentiometer, less and less, up. Oh, you see how it works. So at this moment I'm reaching the impedance of the cable, and we have no wave reflected from the end of the cable. And if we continue to move downwards, so decreasing the value, so we have the reflection again, but with the opposite side. It's quite basically you can see how you measure the impedance of this cable on the oscilloscope. It's quite surprising. Okay, let's move it exactly where we have no reflection, approximately here. And now what we can do, we can measure the value of this resistor. And the value is 111.5 ohms. So the impedance of this network cable is exactly this value. Let's discuss our measurements results. So the signal travels around the cable, goes to the end of the cable, and then reflects back to the initial position of this cable. And we can see it on the graph. So this is on the oscilloscope. So this is the initial moment when we have the signal coming to the cable. You can observe it. Then we have a plateau. Signal goes like this, and then we have a bump. Signal goes back to the initial position. And we have a bump because it's not actually a pulse like this, but it's a step. Step is pretty long. It's 100 kilohertz. So we have it constantly on, and then it goes back to the initial position, so we have extra signal on top of it. Okay, so the length of the cable is obviously the length that signal is going to take. So 1/2 of this distance multiplied by the propagation time, delta t, and multiplied by the speed of propagation, v. So the speed of propagation, we can derive this from the transmission line equation. So if you do the math and solve the wave equation, you're going to have this thing. and the propagation speed is proportional to the 1 over square root of inductance per unit length multiplied by the capacitance per unit length. And so this will reduce to the speed of light divided by the properties of the square root of the dielectric permittivity of material multiplied by the magnetic permittivity of the material. And the speed of light is 1 over square root of epsilon naught mu naught, as we all know. So eventually we're going to have this term. So this one is usually equal to the dielectric property of material is actually equal to 2 for the most of the claddings. And as the result, you're going to have the speed of propagation equivalent to 0.7 speed of light for the regular type of materials, dielectric materials. Well, in any case, you can look up the cable specification and find the velocity factor or speed of propagation, or you can measure it. You can measure it by taking a small sample of the cable and running the measurements. I'll talk about this a bit later. But at this moment, I'm going to keep this number. So we have the speed of the signal inside the transmission light is equivalent to 0.7 speed of light. Now let's talk about the oscilloscope. So what it does, it takes measurements, and the frequency at which it takes measurement depends on the number, which is called number of samples per second. So if you, for instance, have a oscilloscope with 1 gigasample per second, it's a quite regular, not expensive oscilloscope. You're going to have measurements happening every 1 nanosecond. So every 1 nanosecond is going to take measurements. Now we can ask about the distance the light is going to travel during this 1 nanosecond. So we know that the distance is equivalent to the signal speed, 0.7 multiplied by speed of light. It's our speed of propagation, multiplied by the time of propagation, which is 1 nanosecond between those two measurements. And you plug the numbers, you get 20 centimeters. So meaning that oscilloscope making measurements, and then the light after each measurement can escape 20 centimeters from the original position before the next measurement is taken. So we have those jumps after each measurement. Okay, so now you have to ask question what kind of cables you can measure, and that depends on the accuracy you want. If you like to have accuracy, say 10% accuracy, meaning that you have to have at least 10 measurements. So for instance here, you have to have 10 measurements done before the signal come back. You can have more measurements. So if you have a longer cable, this bump is going to happen later, so you're going to have not 10, maybe 100 measurements. But the minimal number of measurements is only 10. So if you have 10 measurements, you can expect to have accuracy around 10%. Okay? So after 10, if you have 10 measurements and the signal is going 20 centimeters after each measurement, then you're going to have 2 meters. So the signal, the light is going to, not light, but signal is going to travel 2 meters in one direction. Thus, because the cable is half of the distance, you can have the cable, this length is only 1 meter. So meaning that you can play with cables 1 meter long if you have 1 gigasample per second oscilloscope. So I think I will stop at this moment. I only just say that for the measurements of the cable, you don't have to have an expensive devices. Any oscilloscope will do. So this one is 200 megasamples per second only. It's good enough. Any multimeter is good enough to measure the potentiometer value. So you need to have only basic devices. I like this device because it has connection to the computer, so I can look up the graphs. Beautiful graphs on my screen. And it also has a generator, so I can use generator from this device to drive my cable. So this is the very simple cable, and it's also good enough to do the measurements and experiments. So you can take any devices you have and you can do your own measurements and see what's going to happen. And you can actually do a lot. For instance, for this cable you can find the length of this cable, or if you know the length, you can find the propagation speed of this cable. You can also find the impedance of this cable using multimeter. And you don't have to solder anything, you just can grab a breadboard and connect the wires through this board, use a regular potentiometer. And it's amazing that this simple setup is sufficient to measure speed of propagation. And one more thing, after realizing that you have almost any oscilloscope to test the cable length or signal speed, I decided to go even to the lower end, and I have this oscilloscope, it's a portable one. It's a good oscilloscope, it's inexpensive, around $50 I think. So what it has inside has generator to test the probes, so you can tune the probes to have the right response. And it has a single channel, so we connect this generator to the cable, so we can drive the cable, and this cable goes back to this oscilloscope. And what I see nice, beautiful pulses. So, but let's go a bit low in time. Let's zoom in. So, nanoseconds. And now we can see the similar picture. Oop. So that's a very familiar picture. You have this plateau, meaning that the signal is going to the cable, and then it reflects back to the original position. So we can measure this distance to measure the time needed for the signal to travel through the cable. Now we can measure this distance precisely. The resolution is pretty good. I think it has a higher sampling rate than that one. And the best thing about this oscilloscope is that it's portable. So you can take it anywhere. Let's say you can take it in the fields and measure some cable down there. It has the internal generator, not designed for this purpose, but useful calibration of this device. But you can use it to test the cables. So this is amazing result. And when I started this project, I thought that probably you need to buy, or you need to have some expensive oscilloscopes with high bandwidth and high sample rate, but no, the most simple one is good enough, even this one. And I also have done the calculation for this cable, so the time duration for the signal going through this cable and back is 486 nanoseconds, and that's meaning that the cable length is 49 meters, but I thought that I bought 30 meters for this cable, so it's almost twice the length. So I started to look at the marking on this cable and I found this. So it says 50 something, like I add the M here, but it's just 50. I'm not sure what this means, so maybe I bought 50 meters, but anyways, expectation was that I have 30 meters, and after the measurements it appears that I have almost 50 meters of cable. So profit. You do the measurements and you get extra, and I think it's 50. It feels like 50.